Next will be Rincon Corporation and John Wallace. So he's going to talk to us about their Raptor SDR development kit.
Okay, so I'm from Rincon Research Corporation, and I brought my colleagues with me. Pat Ellis in the back, he's the director of our Colorado operations, and Troy Grossarth is an engineer right here across the street in our Colorado Springs office. Next, please. So to give you a little bit of a background on Rincon, we're a group of engineers and scientists, and we're really focused on doing cool stuff with radio waves, signal processing, and computers. So we love all these RF techniques for PNT. We're about 200 people. We were founded back in 1983 by Dr. Michael Parker, who was named as a pioneer of national reconnaissance by the NRO. We have a worldwide presence at a lot of different government facilities, and we're focused on the defense and the IC. It's kind of our main areas we support. Again, I said our core competencies are in RF applications. That definitely includes PNT algorithms. We understand basically every PNT RF-based algorithm that's out there right now. We do research on GNSS technologies actively since the company's been founded. We develop our own software-defined radios, and we use software-defined radios to acquire those signals and process signals. We do lots of different digital signal processing stuff, so things like how can you extract your signal when it's being jammed? How can you mitigate interference? What clever techniques can we apply to help mitigate that stuff? There's FPGAs that are a good resource for us for taking those algorithms that we have and putting them into something that has a lower size, weight, and power that's a little more specific to the mission you're trying to do. Lets you put it on a small platform where you have less power, less size available. And then as the mission changes, you can load in a new FPGA image and keep rolling. We've got experience integrating systems and supporting things operationally. And you can see our facilities with our Colorado Springs office right across the street. So I've got two concepts for you today. One is about doing navigation with signals of opportunity, and this is an RF-based technique. And the other one is going to be about time transfer, because as we were hearing before, let's say GPS is denied to you, you're going to lose both of those things. You lose your ability to do precision timing, and you lose your ability to do navigation. So one of the things we want to do is show not just these concepts, but we want to show hardware that's available today that can help demonstrate those concepts and put together some prototypes. So let's pretend we have a system up here in a UAS, and it's got a software-defined radio on it. So that's a radio that some days it listens to, let's say, coastal radars, and then you can put in a new program in it, and it's going to listen to cellular base stations or something like that. Or you put in a program where it's going to do Spectra monitoring on all of those signals at once. So we have a software-defined radio in the UAS, and it has an antenna and it has the frequency coverage where it can hear all of these different signals at once. And not only signals on the ground, but signals up in space. Because if GPS is denied, perhaps not all the communication satellites are denied. There's a lot of satellites up there. Let's hit next on that. So we're going to make a couple basic assumptions here that we know the location of those terrestrial sources. So if there's a cellular base station, we know where that is. We're going to say we know the orbit of the satellite that we're trying to use. And that's something that Rincon has a lot of experience doing. And we're also going to assume that the transmitters that we're listening to are stable in terms of their frequency. They don't have to be accurate. They don't have to be all derived from a GPS receiver themselves. But we're going to assume that they're pretty stable and they're doing whatever they're doing, even if it's not totally accurate for us. So taking this concept, knowing where those terrestrial sources are, we have a lot of experience doing geolocation based on RF. And we have a lot of experience doing very high precision, high accuracy orbit determination. Next. So why are we going to combine those things? Well, one is because it gives us more signals to work with that probably are not all denied at once. And it gives us better geometric diversity. So if I'm listening to things on the ground, I'm listening to things in space, I can resolve my altitude with better precision. And it gives us more robustness to jamming. So how are we going to do all this? we're pretty good at looking at the externals of a signal. So that's features that are in the signal itself that aren't in the data that the signal is trying to convey. We can extract some of those features and do techniques on to recover timing or to line up different signals, measure the frequency of a signal very precisely, and do frequency difference of arrival techniques. Most of these techniques don't involve actually demodulating the content of the signal, so we're not going to be spying on people, right? We're going to be using features inside the signal that don't require that demodulation. Next, please. So you could put this RF package, it's small, it's lightweight, it's low power, it's reconfigurable. We just heard how important that is. We don't want to solve today's problem or tomorrow's problem, but we need to be thinking pretty far out. The good thing about RF is it works all weather, day, night, all that stuff, foggy days, not a problem. And we're going to be operating passively. We're not going to be emitting our own RF signal that can be located or jammed or anything like that. Next, please. So this is the frequency Spectra chart. If you come to Rincon's offices, this is in a lot of our offices because we're all RF engineers and we like this chart a lot. So GNS, pretty small chunk of the spectrum, right? So that makes it easier to jam. Next, please. So color didn't quite work on here. Sorry about that. These other ovals are just a couple signals we've identified that are kind of easy to work with. There's lots of stuff out there, and these are within the range of the radios that we're talking about today. These are signals that have that timing characteristics that we can easily work with. So it covers a lot more frequency. It's harder to jam. It's more ubiquitous in terms of it's used in this area, it's used in that area. It's not localized to the US or something like that. Next, please. So how would this system work conceptually? If we're talking about that airborne application, we could do a demo with our Raptor radio there. It has two channels, two receive channels. So we'd have one antenna looking up, hooked up to one receiver, one antenna looking down, looking for those cell base stations and digital TV transmitters and stuff like that. We would also be bringing along a timing reference. Now our favorite timing reference is, of course, the GPS Disciplined Oscillator. Now, I know that sounds like I got the cart before the horse there, but these now have these chip scale atomic clocks, which I think our friends after me will be talking more about, which have excellent holdover. So you can get everything all synced up. You go into a denied area, and we're going to keep freewheeling, but do that with high precision and accuracy. So that'll keep our radio well referenced. We have the signal processing chain inside it, where we have a kind of a wideband front end that can look at multiple signals, and then we can identify each one of those and do some signal processing on it, do some time frequency estimation, and stick that out into a Kalman filter. We can scale this up to cover more frequency by providing more radios or providing wider band radios, stuff like that. All right, so we talked a little bit about how we're going to navigate using those signals of opportunity around there. Time transfer, though, we still need that. There's a lot of applications out there that need precise timing, and we're talking microsecond, nanosecond kinds of stuff, right? If I'm in that denied area, I don't have that anymore. So one of the concepts we put together is being in a friendly location here, transmitting up a timing waveform to something like a geosynchronous satellite. So that satellite more or less looks like it's sitting right above the area of interest or sitting in a fixed location around that area of interest. And it's going to retransmit that signal down to the area that we're operating in. So we have some hardware that could do that. That's called our Astro SDR. That's very similar to the Raptor software-defined radio we just talked about. And it can relay those timing signals down there so that we've got that. Let's hit the next slide. So we understand the waveforms that you would want to produce to make a good time frequency reference. You can transmit those from that friendly area and then have the Astro SDR be reconfigurable because different areas might have different jamming operations or different denial attacks going on. And so you need your relay up in space to be agile so that it can change and adapt to that. And that's something that software-defined radios and FPGA-based software-defined radios do really well. One thing you need to know is the precise orbit of that geosynchronous relay, and that's something we've got handled. And then let's say your receiver on the ground that needs that precision time is moving. Well, now he needs to know how he's moving as well as hearing that timing signal. So now we're going to combine both of these concepts and say, well, we can navigate using those signals of opportunity, and we can hear our time transfer signal, and now we've got both. And that's all I have for those two concepts. Feel free to contact us and questions.
What is the initial timing signal? How does that get established?
Okay, yeah. So you're talking about in the time transfer?
Yep.
Okay, so we would since that's in a friendly environment, assuming the whole constellation isn't unavailable, we would probably use GPS for that. Yeah. There's other options, and depending on what you need there, we could have some very stable frequency sources too. So.
When you talked about accurate satellite orbits,
Mm-hmm.
can you comment on what your source for those orbits are and how accurate of information you're looking at?
Can I comment much on that, Pat?
Okay, just curious.
So we have a system that does passive RF location of satellites. So it's similar to long baseline interferometry, and we have a system up and running that we can do demonstrations with that uses those facilities we have there. We've got one in Virginia, one in Denver, one in Tucson. That's establishing that long baseline. Those are synced up by, you guessed it, GPS, and we're doing orbit determination that way.
So you're I didn't know if you had a source you were getting this from. You're determining
Nope,
yourself.
we can do that ourselves, yeah.
How long are you able to operate in a GPS-denied environment using those CSACs?
That's a good question. It would depend on the accuracy requirements you have. And to be really honest, I know they're really good in terms of how well they freewheel. I don't know how good that is. I don't have that off the tip of my tongue. So I don't really want to hazard a guess, but that would certainly be one of the things we'd be interested in evaluating really clearly. Thank you very much.